Okay, our final paper of the morning is a contribution from Iowa State University and the Ames Laboratory of the Energy Department. And as many of you know, for years, Glenn Schrader and Dr. Glenn Schrader and Robert McCarley have been interested in these Mo6S8 clusters. And today, Thomas Paskac, who is a colleague of theirs, is going to present a paper on some of their newest findings with these Mo6S8 clusters. Thomas.
Thank you. It's a pleasure to be here, and thanks to Cal for accepting our research for this presentation. Like you said, we've studied these cluster compounds, the Mo6S8 cluster compounds as catalysts. We've broadened our scope. We used to study these compounds for HDS, and we've turned the tables a bit. And we've been looking at thiol synthesis and more in general, organosulfur compound synthesis. I'll start with a little brief outline of what I'm going to talk about today. And first of all, I'll give a bit of background for those who aren't familiar with these materials. And we'll talk about the structure and the types of materials that are possible to synthesize. And I'll go a little bit on how you actually go about that in the preparation method. Again, as I mentioned, these materials have been applied to HDS in the past. And we'll also talk about our work more recently in the area of thiol or mercaptan synthesis. So then I'll go kind of into our results section. This is, like I said, our recent work is a methane thiol synthesis over these materials. And we've looked at, there's a wide variety of these materials, and we've looked at these for its thiol synthesis in terms of their activity, selectivity, and stability. And then we've chosen some that look more promising, and one in particular that wasn't, to compare more in depth. What are the major factors that influence their activity and selectivity with respect to temperature? And an important variable in this is the hydrogen sulfide to alcohol ratio. Alcohol is the feedstock that's generally used for thiol synthesis. The materials that are based on Mo6S8 cluster include the well-known crystalline Chevral phases. And these are, I list just the formula. You have a ternary metal that exists along the Mo6S8 cluster. The Mo6S8 cluster itself is an octahedron that's kind of stretched of molybdenum atoms, and you have bridging sulfur atoms on the squares that form a cube. We also have terminal sulfur, or in the case of molecular clusters, where these compounds can be made as single molecules and crystallized and isolated. A ligand, such as pyridine, piperidine, etc. Usually it's a nitrogen-containing or basic ligand that is joined to the faces of the cube. And like I said, the ternary metal that can be incorporated here, and especially in work that was done by my predecessors in this area, the amorphous ternary materials are made, and there's extra sulfur in these materials that balance a little bit of the formal charge of the ternary metal. And we consider the formal charge in the Mo6S8 cluster to be neutral in these materials. And so we've incorporated metals such as lanthanum, tin, palladium, platinum more recently, cobalt, holmium, and also lead. Well, to prepare the amorphous or higher surface area materials, we go through a two-step procedure, and we start with the preparation of we call a sodium starting material. We start with Mo6Cl12, which already has this octahedral structure in the Mo6 cluster. We react that with a sodium hydrosulfide and an alkoxide, a sodium alkoxide, normally it's ethoxide, and refluxing butanol. We end up with a ternary compound that has a sodium balancing an extra sulfur. And this is an amorphous compound with surface areas that can be as high as 200 meters squared per gram. There's also produced as a byproduct sodium chloride and alcohol. And then what you do is you take that sodium starting material and react it with a metal salt in an ion exchange reaction, and the metal salt replaces the sodium, and you end up with a ternary amorphous Mo6S8 cluster compound. And this retains the high surface area that you see in the sodium starting material. If you want to produce these ligated molecular compounds, you can actually produce those as a ternary compound, but also you can produce the single molecules. And what you do is add the ligand to the first reaction, and you form a ligated sodium-containing amorphous material. And if you reflux that in excess ligand, you can actually obtain and isolate soluble single molecules. Well, our work, as I said before, falls into the general broad topic is organosulfur catalysis. And we've been doing hydrodesulfurization with these materials for several years. And more recently, we turned to organosulfur synthesis. Organosulfur synthesis includes in commercially production of mercaptans, alkyl sulfides, polysulfides, and thiophenes. And they're useful compounds, and they're kind of like fine chemicals. And they're used in the production of odorants, agrochemicals, pharmaceuticals, and also model compounds for HDS. So, what we've looked at is, in particular, is methane thiol synthesis, and starting with methanol and hydrogen sulfide over these materials. The first three reactions that are side reactions to the main reaction are alkyl sulfide synthesis, hydrogenolysis of the alcohol, and esterification. These are the main side reactions that are reported in the literature over like cobalt, molybdenum catalysts, and others similar to the HDS catalyst families. So these are the only really important side reactions that are reported in the literature. Over our catalysts, we see additional side reactions. We see the formation of carbon disulfide. We see significant formation of carbon monoxide and carbon dioxide, and even carbonyl sulfide. And we always need to allow, I guess, for the composition or decomposition formation of coat. In order to evaluate our catalysts, we constructed a microreactor system. And it's kind of a standard microreactor system. We have mass flow controllers for the gas speed, so we have very precise control over gas speeds. We use a saturator to deliver the liquid feed as a gaseous liquid. Anyway. And then the catalyst sits in a furnace, and we have a helium to add to the reactor effluent as a diluent, so we can prevent condensation of reactor products. And reactor effluent lines are all heat trained. An online GC is installed that collects the data. And in dealing with hydrogen sulfide in a university setting, safety is a primary concern, and I actually had some industrial experience in hydrocracking and hydrotreating, and so I insisted that we follow some safety guidelines to do this work, but we've installed shutdown systems with H2S monitors and alarms, and also extensive standard operating procedures, and then we always use a buddy system anytime that we go to open the cylinder of H2S. I should say that this little section that's right here was used for collecting samples and identifying GC peaks by GC mass spec. So, the initial results we got in studying the various materials that were possible, and this kind of gives you a list of what materials are possible and which ones we evaluated so far. But in the top of the table, where you see there's extra sulfur after the Mo6S8 in the formula, these are the amorphous ternary materials, and they all have fairly high surface areas, as these are unsupported catalysts. And then we have next would be this would be the starting material for the molecular cluster compound, so it has a pyridine ligand. And then we have the lanthanum chevrel material and a couple of molecular complexes, and MOS2 as a reference. And what we see, a couple of things. First of all, we notice that we're in the reaction at 250 degrees C, which is fairly low compared to commercial applications of thiol synthesis catalysts, and a fairly low hydrogen sulfide to methanol ratio. But even at 250 degrees C, we're losing quite a bit of the surface area that we have to start with in the reaction. Another thing to notice is that the conversion rate, or the rate of methanol conversion, is highest on a per gram basis for the amorphous materials, and higher on a per meter squared basis for the crystalline materials, implying that some of the surface isn't really accessible. We should expect kind of similar results, I think, for for those numbers if all the surface was the same, especially comparing the lanthanum material, Chevral, to the amorphous material. This is an extension of the last table, and what it is selectivities and the products and the major side products that are produced in the reactions. And what you see right away is that selectivities to methanethiol are pretty reasonable and fairly high for lanthanum and holmium. And these are the large ion type. If they were Chevral phases, they'd be called the large ion type Chevral phases. And then the smaller ion types seem to have a little bit lower selectivities. And probably the other main thing to notice is that we have significant selectivities to these carbon oxide, CO2, COS, and CS2. So kind of put it in the back of your mind, if there was a way that we could eliminate this type of chemistry, which really isn't observed in the commercial catalysts, that these might be very selective catalysts indeed. Well, we're also interested in the stability of these materials under reaction conditions and beyond just the surface area decreases. So we look for degradation of the material to MOS2, and we use laser Raman spectroscopy to do that since it's a very sensitive technique for detecting MOS2 formation. And what you can see is the bottom trace is MOS2, and what we look for is two peaks, two Raman bands, one at about 383 and one at about 404 wave numbers. What we can see right away is that these sodium materials show formation of MOS2, and this is after 20 hours at 250 degrees C. We also see a little bit in the tin and maybe a little bit in the platinum. The lanthanum Chevral phase showed no conversion to MOS2, and neither did these ligated molecular complexes, which is a bit surprising, since 250 degrees C is above the minimum temperature required for deligation. We have some prior results that show that deligation will start below that temperature, but no conversion to MOS2 is indicated. And also, these large ion types of holmium and lanthanum amorphous materials didn't show any formation of MOS2 under those conditions. So now I'll switch. We're interested now in the lanthanum material because of high selectivity and stability. And, we're also interested in those sodium materials because they tended to convert to MOS2 rather readily. So we did some more in-depth studies over these materials and looked at kind of the effective temperature in the range starting at the lowest, which was 250 degrees C, and then increasing the temperature. As you can see, we can increase the conversion of methanol to nearly complete conversion at 350 degrees C, which is a pretty close to relevant industrial temperature for these reactions. And the stability, you can see there's still some slight deactivation after 3 days online. And the selectivity to methanethiol under these conditions too, it's interesting. It actually increases at the beginning of the reaction and then tends to stabilize. And notice also that the selectivity, as we increase the conversion by raising the temperature, the selectivity to methanethiol decreases. I have a summary of those results on a table in a second. In comparison, the sodium, this ligated sodium material that showed some degradation to MOS2, the same experiment was carried out. We could never get, even though this material had initially pretty close to the same surface area, we could never get as high of conversions with the sodium material. And the selectivities here are lower also. What's interesting here is that they stopped, selectivity didn't decrease anymore after 300 degrees C in this reaction. So this table kind of summarizes the last 4 slides of those experiments versus temperature. And what I want to point out here is a couple things. First of all, as we increase the temperature from 250, 300, 350, we lose more and more of the surface area of the starting catalyst. So we'd like to find a way, if we could, to stay at a lower temperature to maintain a higher stability in these catalysts. Another thing I want to note too was that even though our conversion conversion, at 250 degrees C is fairly low, 9%. Our contact time on these catalysts is very short, on the order of 1 second. And commercially, this reaction is actually carried out in the liquid phase and given contact times on the order of hours. So this may not be as bad as it looks as far as activity. The second thing is to look at what's causing the decrease in selectivity. And it looks like down here, it's not the traditional byproducts, which would be dimethyl ether and dimethyl sulfide. Those remain fairly constant over the whole temperature range. What's happening is we're forming more of these single carbon, like CS2, CO, CO2, and COS, especially CS2 and CO2 in the case of the lanthanum material. So again, if there was a way we could eliminate production of these products, we would have fairly selective catalysts. In the sodium material, it's the same type of trend. In here, there's a shift from CO2, COS production and CO. So it looks like a little bit of CO to COS, and that reaction actually is catalyzed by this material too. If you feed pure CO and H2S, you form COS. And so it looks like, again, here, it's this type of, the chemistry that's going on between these compounds is what's important. I also promised we talk about the variable, which is hydrogen sulfide to methanol ratio. If there was a way to reduce the amount of hydrogen sulfide you need, you could think about increasing the safety of the process. And so we're interested in how much hydrogen sulfide you really need to get this reaction to go. Patent literature, they claim up to 18, as high as 18 I've seen as far as the mole ratio for this variable. Stoichiometric ratio is 1. So what we've seen is, this is after 3 days, and then this experiment was carried out. What we've seen as we increase the hydrogen sulfide ratio, we actually decrease the rate of reaction, implying that it's a very strongly absorbed reactant, hydrogen sulfide is. The other thing that's of note is that we really don't start to drop significantly on the selectivity to methane thiol until we get well below the stoichiometric ratio. In other words, at 0.5 to 1, which is stoichiometric ratio for dimethyl sulfide, we're still producing nearly 70% methane thiol. What's also of note is that since this isn't a really dramatic maximum at 3 to 1, what's causing it is an offset between the selectivities to CO2 and CS2. At the same time, the CO2 selectivity is dropping as hydrogen sulfide increases. The selectivity to CS2 is increasing. And those two tend to offset each other, and so we only have a slight maximum at 3 to 1. So it seems like the reaction is fairly insensitive to this variable as long as you're up above about 1 to 1 ratio. Again, we're interested in the stability of the catalysts. We carry out catalyst characterizations after these reactions. We looked at the pore structure using nitrogen absorption analysis. We also looked at the infrared spectroscopy, laser Raman spectroscopy. These were kind of in search of MOS2. And then some X-ray photoelectron spectroscopy to try to determine what is at the surface. In looking at the pore structure, before and after reaction, the round circles are post-reaction. And then we have pore diameter versus pore volume. And so what you can see is immediately we're losing pore volume associated with the small pores. And so it's the small pores that are collapsing under reaction conditions. And this was 72 hours. I didn't write it, but it's 250 degrees C also. By laser Raman spectroscopy, again, we showed the sodium material, and you can see a little bit of MOS2 at 250, but it becomes very apparent at higher temperatures that the sodium material tends to convert somewhat to MOS2. This isn't, I should point out that the laser Raman spectroscopy is very sensitive, and so it's not full conversion to MOS2, but it's pretty clear that that's what's happening. Now, raising the temperature with the lanthanum material, we also start to be able to detect MOS2. And even if you're creative, you can see a peak here at 250 degrees C for MOS2. But then again, by 350, it's pretty clear that by laser Raman we can detect MOS2, even on the lanthanum material. Looking at these catalysts with FTIR, what we look for here, the bottom trace is for pure MOS2, and you can see a peak at 470, and then a band at 385 for MOS2, and it's this sharp band here. In the as-prepared material, there is, in the literature for these Mo6S8 catalysts, there is an MOS stretch in the range of 385, but it's very broad, so it's a little bit difficult to see. When we've looked at these materials with XAFs and determined the structure fairly clearly with crystal materials at least, and also the amorphous materials. But as we raise the temperature, again, it's the same picture as that was shown on the laser Raman, that at 300 and 350 we can start to pretty clearly see this band at 470, indicating that in the bulk that we're starting to get some MOS2 formation. Now, I mentioned we're interested in looking at the surface of the catalyst using XPS. And what we look at here is the molybdenum 3D region. In the as-prepared material, we have a pretty low binding energy for molybdenum, and it's usually around 227.9 or so electron volts. That's characteristic of molybdenum in the cluster. As we put the catalyst in the reactor and raise the temperature, and this is again after 72 hours, we see a shift to higher binding energies in the molybdenum environment. So we're definitely seeing a change at the surface of molybdenum. And what we do with the XPS data is we do our deconvolution of the MO region. And in the MO region we have sulfur 2S we throw out. It overlaps a little bit. And then we use symmetric peaks and fix the offset and area ratios, etc., to deconvolute these peaks. Try to sort out what species are there and in what proportions. And so this is a summary of the characterization of the two materials, lanthanum, this is amorphous lanthanum polysulfide, and the sodium, pyridine ligand sodium channel. And what we see is, as I showed in the last slide, we see a shift to higher binding energies, and what I have kind of assigned this to is what I call an MO3+ species. And why I've done that is because the binding energy is really a little bit too low for us to consider it as MOS2. Normally MOS2 is around 229.5. Some papers have shown it as low as 229.0, so you could argue that maybe this is starting to look like MOS2. But it is it's a reduced, it's a very low binding energy if it is MOS2. What we see is at 250 degrees C, it's clear, it's easy to see that there is some MO4+ formed, and that's true for both these materials. But then as we raise the temperature again, during the deconvolution, the fit really is best if you have really almost completely this MO3+ species. So we're interested, that's kind of strange, what that intermediate oxidation state is. I should mention at this point that we have seen that kind of an intermediate oxidation state in that binding energy too in some HDS work on these materials. So in order to get at what this intermediate species was, we did a couple of experiments where we started with amorphous lanthanum monosulfide and treated it with either just methanol in helium or pure hydrogen sulfide, and temperatures up to 400 degrees C. And with pure methanol, we saw really no oxidation of the surface, at least detectable by laser Raman. And what I can see is a slight amount of MOS2 being formed at 400 degrees C when it was pure H2S. Couple that result with XPS results in the same experiments. And what's interesting is that when you treat the material with just methanol, the cluster, the peak responsible for the cluster remains even up to 400 degrees C, and none of this intermediate oxidation state is formed at all. we show only MO4 plus and a little bit of MO3. But if you treat it with just pure H2S, then this MO3 plus intermediate oxidation state is pretty readily formed, and it becomes the prevalent surface species. And that to us is two things. One, that this intermediate species must be a sulfide species, and it also requires gas phase H2S. It's not just disproportionation of the material itself. Well, that takes care of our methane thiol, and I have one slide to tantalize you with our more recent results with butanol. Turns out we can eliminate that carbon oxide, carbonyl sulfide, carbon disulfide. There are no analogs to those compounds in the C2, C3, C4 alcohol game. So what we do is just use a higher alcohol, and I actually was able to obtain pretty high selectivities to the primary butane thiol, and again, fairly low ratios of hydrogen sulfide to butanol. So I still think these are pretty promising catalysts for thiol synthesis. This is starting to get very close to the most recent patented selectivities. So what we can say is that the materials based on the Mo6S8 cluster, which we've known for some time and studied and shown they're active in HDS, are a new family of thiol synthesis catalysts, and they're active and selective at fairly low temperatures. You might have noticed on the butanol that it was 200 degrees C, and I've done some work with other alcohols, and they're also active at lower temperatures. The most active and selective and stable of these materials for at least methane thiol synthesis were the amorphous ternary materials, where they were the large ion type, lanthanum and oleum. We also have seen evidence by XPS of a surface oxidation state that's intermediate for molybdenum, and that's the main species of molybdenum present at the surface. And just finalize, or the final conclusion is that we feel like these are particularly promising catalysts for application to the higher alcohols, since we can go to even lower temperatures, and their activity or stability should be enhanced by the lower temperature. I'd like to acknowledge our support by Department of Energy's Ames Laboratory and Iowa State University. That's all. Thank you.
We have time for a few questions, but then there's a little bit of business I also want to get to. So, Martin?
I just wondered if you had done an experiment with no catalyst in the reactor. The reason... Okay. And maybe you could comment on what I was going to say. I noticed that when you compared the catalysts with high surface area to the ones with very low surface area, the crystalline ones, you had more side reactions. You don't have to get it out.
Okay.
And so I wondered, and I also noticed that when you went to higher temperatures, the surface area of the high surface area catalyst decreased. So I was wondering if there's some thermal reaction occurring in parallel to the catalytic surface reaction, and that's why I asked if you had done an experiment with no catalyst in the reactor.
Yeah, when there's no catalyst in the reactor, nothing happens. There's no conversion to anything. No. Right. It stays the methanol. You just detect methanol and no other products.
If you plot yield versus conversion,
Okay.
can you tell if the undesirable products are secondary products?
I guess I haven't done that. I guess that would be something interesting to try. I think I've fed, when you feed just methanol without hydrogen sulfide, you do form these products. The GC was on while I was doing this treatment experiment, and you do form the CO and CO2 compounds. So.
Yes. Question over there.
Very interesting presentation, thorough characterization study, very impressed. A couple of questions for you. One is, in case of butanol, you mentioned the conversion is very high, the selectivity to butane thiol is pretty high, about 95%. I was wondering if you have observed any catalyst deactivation when you ran for a long period of time.
Yeah, okay, The catalyst, again, what you normally see is an initial quick deactivation loss in all cases, and even at the lower temperatures. I'm not sure what's causing that. I guess it could be partly due to just the initial stabilization of the catalyst, but after that initial deactivation occurs, then it remains stable, and at the lower temperatures under with butanol, it remained much more stable.
How long?
I've never taken it past 3 days, but pretty flat line. Yeah.
The second question is, you mentioned about the selectivity for methanol using sodium Orgaonsulfur catalyst. The graph that you had is for the temperatures 250, 300, 350. And for 300, 350, your selectivity to start with goes in opposite direction. One is going down, stabilizing, the other one is going up and stabilizing. I was wondering if you can explain that.
I can't explain it.
It's a little bit.
And what I can say in those, let's see. Are you talking about the I know what you're talking about. This one?
Yes.
Yeah.
Yes.
I think, yeah, it's a battle between carbon disulfide and carbon dioxide as a major side products in this reaction. And I'm not sure if the initial, I've done a lot of studies with the thermodynamics of the reaction, looking at carbon disulfide. Carbon disulfide is a compound that's really not stable at the higher temperatures. And so comparing the one at 350, it may be that I don't know if I have a complete definitive answer for you. Like I said from the beginning, I can't explain it. I haven't been able to explain it. I guess the initial, what's happening in the initial stuff, I really haven't studied that much. I've mostly tried to stabilize the catalyst and then try to rationalize based on post-characterization what the results mean. But you're right, there's definitely something going on here.
Have you tried the second time just to see if it's the same effect or different effect?
Second time
Not the same experiment another time?
with the same catalyst?
Yes.
Oh, yeah. If you stop and start the reaction, basically, once the catalyst is stabilized, you start right back up where you left off, essentially.
Okay, one more question for Professor Hoffman.
You can obtain with very high yield the mercaptans or zero life catalysts with acidic version. You take the fungicide with 100% So my question is, did you compare the performance of your catalyst with the zero life?
We're interested in the performance of the catalysts as far as overall yield, of course. What in the most recent patent literature, probably the most promising are these potassium oxide promoted tungsten alumina, and also, yeah, that's really the best one. And they can get fairly nearly 100% conversion. But again, the reaction conditions of those, and I'm not particularly, I know exactly which literature you're referring to, but I think part of the reason might be the fact that we have a gas phase reaction that's occurring at low pressure and also very short contact time. So the only way I can boost my conversion is to crank up the temperature, and that's really not the way you would want to do it if you want to maintain selectivity.
Okay, thank you, Thomas. I have to admit, the reason I chuckled at Thomas's answer to Martin's question is Thomas is expecting to get his PhD for this work, and I remember when I was going through my own defense thesis, my research director gave me, very strict instructions. You can answer a question yes or no, do so. Don't elaborate. One question, there's someone missing from this afternoon's session from Argentina. Does anyone know of or has seen Annunziata Pereira? Leda? No? We got the CV. Sorry?
What is the paper number or what time?
The paper is at 2 o'clock.